Good afternoon everyone. Thank you for joining me for today's video on analyzing trigonometric functions. I'm Mr. Ish. Today should be an interesting topic. Here I have drawn a standard single period of a sine wave. I could have used a cosine wave, but I just chose to use a sine wave. I want to examine everything today in terms of analyzing based on this equation we see over here for a trigonometric function, focusing particularly on sine and cosine. Because the sine and the cosine functions are more commonly seen in applications, it is more important to be familiar with the sine and the cosine function analysis. Here, this sine could have been easily replaced with a cosine, and everything I'm going to talk about would have remained the same for the most part. The specifics with regards to the graph points would have changed, but generally everything else would stay the same. So with regards to this function over here, if we just look at this single point from right here, 0 up to 2 pi, this represents a single wave of the sine function, the start and the end of a single wavelet. You know the sine wave and the cosine waves can continue indefinitely in either direction to include multiple waves, millions of them if needed. If you're looking at one start point to one end point, that represents a single period. Sine and cosine waves in general have a period of 2 pi. Over here I've written 2 pi. That is the interval of the start of a single wave to the end of that same wave is 2 pi. Meaning it's 360 degrees long. So it starts at 0 and ends at 2 pi, assuming there is no shift. And let's look over here, amplitude. Amplitude is related to the volume. You know, like when you turn on the volume of a radio, what are we doing? We're making the noise louder, the music louder. That is dependent on the amplitude. The amplitude is basically the height of your function. You know, in general, sine and cosine have a range of from -1 up to 1. They go no further below -1, but they go no further above 1. See, they have a range of -1 to 1. If we don't affect the amplitude of a function, of the sine and the cosine function, we'll always have an amplitude equal to 1. I'm going to be talking about all of these letters over here momentarily, but I'm just giving a quick overview before we get deep. The domain. Sine and cosine waves have a domain of -infinity going up to positive infinity. See, from -infinity up to positive infinity. If you were to continue this, it would have a domain of all real numbers. Another thing to be wary of is the frequency of a wave and the wavelength of the wave. The wavelength I've kind of touched upon in terms of the length or the period. The wavelength is basically how long a single wave is. If you look at this single wave over here, it has a period or a wavelength of 2 pi or 360 degrees. But the frequency is the number of waves that are present or which pass between a given point of time. If this right here represents a specific point of time, like how many waves will pass through there within that given period of time, that will be the frequency. But there's an inverse relationship between the frequency of a wave, that is the number of waves that are passing through a given point in time, and the length of those waves. You can imagine if a wave is really long, if each wavelet is very long, having a very high period, you'll have fewer number of waves passing through a given period of time or point of time, versus a wave which has a wavelength which is very small. In that case, the frequency will increase. So there's an inverse relationship between frequency and wavelength, which is why X-rays, gamma radiation, cosmic rays, which are high frequency waves, have more energy. Frequency is related to the energy of a wave. They're very small wavelength because too many waves pass through a given period of time or through a given point of time, whereas like radio waves, microwaves, visible light, which have a higher wavelength but a lower frequency, those types of components of the electromagnetic spectrum will have high wavelengths and low frequency. So you know what the electromagnetic spectrum is. It goes from one end, from radio waves, microwaves, all the way up to the other end, to cosmic rays and gamma radiation. And in between you have a relationship with regards to the frequency and the wavelength of each of those spectrum types. So let's look at these letters next. And we're going to do that in a very easy manner. The purpose of this video is not to confuse anyone, but just to give you the tools needed to analyze trigonometric functions. The ability to look at a function, trigonometric function, especially sine and cosine, and analyze its various components is very important. And you can always use a graphing tool to actually come up with the graph, but to analyze the function without without having a graphing tool is actually quite important. If you look at this letter A right here, the letter A, the A is related to the amplitude, and the amplitude is always given in terms of an absolute value. You can't have a negative amplitude, it's always a positive amplitude. Amplitude is related to like the range of that, the height of that curve, how far down to how far above it'll go. That'll be dependent on this A value, this amplitude value. Even if there's a minus sign over here, it doesn't mean you have a negative amplitude. That minus sign would be, if you remember, with regards to the graphing functions video I posted, the negative means kind of a reflection along the x-axis. But we're not talking about reflection here, we're only talking about the A. A, think of that as an absolute value, it's always a positive figure. It's the amplitude of that wave. Next, you want to focus on is this B. The B over here is not a positive or minus value by any means. Don't think of it that. Think of that as a period. The period meaning the length of each wavelet. You want to be thinking of B value in terms of the formula 2 pi over B. It'll give you an indication of how long each wavelet is. And when I say wavelet, I mean a single wave. You take the formula 2 pi and you divide that by B. B here represents the coefficient of whatever your x is. You could have a fraction over here, you could have a whole number, but whatever that coefficient of x is, you divide that from 2 pi and that'll give you the period. When I show you the specific examples, all of this will actually make more sense. Let's look at this whole concept of bx minus c. Bx minus c represents a specific interval. When you calculate this out by the techniques I'll show you, it represents the interval. It'll be the start of one wave, the interval which represents the start of one wave to the end of that same wave. The interval where you starting that specific wavelet and to where you end it. That interval is represented by a specific set of calculations related to bx minus c. There's something called a phase shift. A phase shift is, if you think about the parabolas x minus h, x plus h, it's related to horizontal right and left movement of a wave. Is a wave, is your sine or cosine function shifted to the right or is it shifted to the left? And the degree of that phase shift, you look at this, the ratio of c and b. You see this c and b, you do the ratio of that and you'll get the degree of phase shift. The phase shift can be a positive value or it can be minus value, depending on the direction in which that phase shift occurred. Lastly, think of this as you have in terms of parabolas, the plus and minus k, the vertical up and the vertical down shifting. Well, that's exactly what it is. It is basically the vertical translation. Okay, vertical translation of your sine or cosine function. Normally you have no vertical translation because we've looked at the basic graphs of sine x and cosine x where everything was about the origin with no shifting in any direction. But functions can shift, they can transform, and they can reflect. So we have to keep all of these things in mind. And we will also look at two other items. For each of the examples I'll present, we look at the domain and we look at the range. I'll show you a very easy way for determining the range, which will depend on the combined effect of A and D. And you want to be thinking of it like this: the D minus absolute value of A and the D plus the absolute value of A. And here the capital A and the lowercase a are talking about the same thing, the amplitude. This will give you the lower end of the range, how far low the sine and the cosine function wave went. D plus absolute value of A, the amplitude, will give you how high that wave went in terms of the height. Alright, so keep all of these. They're basically 1, 2, 3, 4, 5, 6, 7 items, but these two items are really part of the same thing. So there are technically only 6 items we need to worry about for each trigonometric function. So let's look over some examples, but remember, all of these will come into play with each question that we'll look at. And anytime you start out with a question, you want to try to convert it into this form, because when you convert it into this form, you get these various aspects clearly laid out from which you can start analyzing your trigonometric function. Of course, naturally it makes sense to start out with an easy example. And remember, I can use sine or cosine for any of these. The purpose of this lesson is to focus on sine and cosine functions because they are most commonly seen. So here we have an example, 6 sine half x. These letters here, x could be a, well actually I shouldn't be saying a, it could have been a t, it could have been a u, it could be any other letters, any other letter which represents a variable other than a, c and d. But I'm going to be using x's over here, and you know f of x always represents a y. Our goal first should be to convert this into this form. And let's do that. We have 6, then we have a sine. Let's create a parentheses. We have a 1 over 2x, which looks very awful close to bx. A minus c, there is no minus c, so let's put a 0. Plus d, there ain't no d, so let's put a 0. Now we can see we have a trigonometric function converted into a standard form with the items laid out. We have an a, we have a b, we have a c, we have a d. Yes, some of these are zeros, but that's fine. By putting it in this form, you have a method by which you will do these following examples. And again, by putting it into this form, you're clearly laying down the components that you need to be examining. So it's always easy to just pick out the values once you've laid them out into a proper form. So let's analyze this specific example. Amplitude A. My amplitude over here, and you can write absolute value of A, should always be positive, is 6. This specific wave, I'm like fiddling here with this number 6. This specific sine function will have an amplitude of 6. It'll go as high as 6. It'll go as low as minus 6. About the x-axis, which represents a 0 value, it'll go 6 up and it'll go 6 down. It doesn't mean that 6 up and 6 down represents a distance of 12. In terms of that, amplitude over here represents the height from the axis up 6 units and from axis down 6 units. So even though the total distance is 12, the amplitude from the x-axis represents a shift, not a shift. It represents a height of 6 in either direction. So think of amplitude like that. That's the height of your curve with regards to the x-axis. The next item we want to be looking at is the period. And let's for sake of brevity from now in this example we'll abbreviate period as just p. P for period. And you know the formula for period is 2 pi over b. I do have a b value over here, don't I? I have a b value over here which represents a half. All we gotta do is plug that half into place of b. We get 2 pi over half. Flip half around, what do we get? 4 pi. We have a wave over here which is not the standard 2 pi period, 360 degrees long. It's twice the length of the standard sine wave. So it has twice the period. So the period over here happens to be 4 pi. Let's look at phase shift. Phase shift, as I mentioned earlier, is C over B. Look at the C and look at the B. Remember, C over B, the phase shift represents has your sine function moved in either direction about the origin. Has it shifted to the right, has it shifted to the left. C is 0, B is a half. 0 divided by half is a 0. So there is no phase shift over here. No phase shift at all. How about this? Vertical translation. Is there a vertical translation? None. There is no. Vertical translation is equally present about the x-axis line, equally above and equally below. There is no movement above or below that x-axis line. So there is no vertical translation of this function. How about that thing I mentioned before? The d minus absolute value of a, which could be lowercase, and the d plus the absolute value of a. This will give you the highest and the lowest extent of the curve. Why is this important? Because this will give us our range. For each of these analyses, we also want to be looking at the domain and the range too. But let's look over here specifically. What's our d value over here? D value over here is 0. What's my a value? It's 6. 0 minus 6 gives me what? A minus 6. And look at this, the highest extent. This right here is the lowest extent of your curve. This right here is the highest extent. So 0 plus a is a plus 6. This is giving me specifically my range. The range of this curve is going to be from minus 6 to a positive 6. And we know that in general the sine and cosine functions go from -1 to 1. Their range is -1 to 1. But by means of this amplitude factor of 6, we're going from -6 to 1. Twice, we have 6 times the height of of a natural sine wave. How about the domain? As far as I'm concerned, for all the examples I'll be presenting you, the domain is always -infinity, infinity, because these waves will extend in either direction towards infinity. The domain will always be all real numbers. The last thing we want to do is determine the interval. You know, remember I mentioned interval as presenting the start of the wave and interval representing the end of that wave. Well, there's a specific way of doing that, and the way is this. You do bx minus c is equal to 0 and bx minus c is equal to 2 pi. But bx minus c is nothing too confusing over here. Bx minus c represents what is right over here. Half x minus 0 equals 0. Half x minus 0 equals 2 pi. All you have to do is solve for that x. If half x minus 0 is equal to 0, you take the 0 on the other side, you get half x is equal to 0 and x is equal to 0. I'm getting my one start of the interval as 0. Remember, I'm doing some of this in my head, but you could have done it easily. Half x minus 0 equals 0 and half x minus 0 equals 2 pi. All you're doing is solving each of those equations out. If half x minus 0 equals 2 pi, take that 0 on the other side, you still get 2 pi. Then you take this 2, which is dividing onto the other side, and multiply, so you get x is equal to 4 pi. Why is this important? Because it confirms two things. It confirms, one, that each wave interval, like the wave interval we have in concern, the main wave interval will start from 0 and it'll go up to 4 pi, but it can also go from 0 up to -4 pi in the other direction. The other thing it also shows, if you were to take this large number and minus it, you get the difference of this, it will confirm your period. Look over here, our period was 4 pi. If you do 4 pi minus 0, you'll get 4 pi, so it confirms. The interval confirms the fact that your period is actually what the interval is. 4 pi over here. So look over here in this example, we looked at the amplitude, we looked at the period, we looked at the phase shift, any vertical translation, we got the range values using this specific formula right over here. Right here, we know the domain is always -infinity, infinity. Lastly, we determined the interval using bx minus c equals 0 and bx minus c equals 2 pi. Solving each of those equations will give you your end point and your start point for a specific wavelet interval. We should be looking at some more examples next, just to make all of this less confusing. I have an example over here. F of x is equal to 3 cosine 2 pi. What should I put over here? Should I put anything else over here? Well, how about 2 pi t plus 2. Remember, I told you could put any letters over here. This is what my function is, 3 times cosine of 2 pi t plus 2. The first thing you want to do is always convert your function given into this form, because it will spread out the things, the components you're interested in. We should start with that. So what do I get? I get 3, I put up my cosine function, then after the cosine put up parentheses. Here's my 2 pi t, and I close my parentheses and I have a plus 2. This plus 2 is not married along with here. It actually represents your d value, your translation. Look over here. I can take this one step further to clarify it even more. I have a 3 cosine 2 pi t minus 0 plus 2. Why am I putting a minus? Because the standard form always has a minus c. So it makes sense to put a minus 0, not a plus 0. It makes sense to do that. So here's my standardized form of this expression, of this function. Outright. You know what? From outright, what we should do? We know for all the examples I'll present you, the domain outright will always be -infinity, infinity. So that's one last thing we'll talk about for these future examples. For all of these examples, the domain is always -infinity, infinity. But the next first thing we want to look at is a, by amplitude. Amplitude is always a coefficient of your sine or cosine function. Here, it's 3. 3 times as tall as your regular cosine function. What's the next thing I want to look at? Period. And I said we'll abbreviate period with the letter P. Period is always 2 pi over b. We know our b value. Here, b value is the coefficient of your variable. Instead of x, I have a t. But the coefficient of this t is not 2. The coefficient is 2 pi. So you can do 2 pi divided by b, which is 2 pi. What does that give you? 1. The period of your wave is 1. Not 1 pi, but 1. You can have a unit of just 1. By having this type of period, you've eliminated the pi from your equation. Okay, but you have a single wave has a unit of 1. Whatever that 1 might represent, the single wave has a period or a wavelength of 1. The next thing we want to look at is phase shift. Should we abbreviate phase shift? Let's do it. PS for phase shift. Phase shift is always C or B. C value 0. B, 2 pi. Remember the coefficient of our variable t or x? Here's a 2 pi. What's our phase shift? 0. Do we have a horizontal translation in either direction from the origin? Is there a translation in a horizontal direction? No. Phase shift is 0. What else do we want to look at? We want to look at that interval, which represents the start and end of a specific wavelet. And you know the formula for that is bx minus c equals 0 and bx minus c equals 2 pi. Well, we know what bx minus c is because it's laid out over here. You have 2 pi t minus 0 equals 0 comma 2 pi. All you gotta do in each of these instances is solve for your variable. Here my variable is a t. Let's solve for that t. When you solve for the t, you'll get an interval. The interval represents the start and the end of that wave. If you do 2 pi t minus 0 equals 0, you take 0 on the other side, you get 2 pi t equals 0. T is equal to 0 divided by 2 pi, and you get a 0 as your start of your wavelet. That's the start of your interval. But if you do 2 pi t minus 0 equals now 2 pi, you take 0, you get 2 pi t equals 2 pi. You take the 2 pi on the other side to solve for that t, you get t is equal to 1. See, you'll get this 2 pi divided by this 2 pi. When you bring it over here, you'll get 2 pi divided by 2 pi, you'll get that 1. And as I said before, the difference of your interval confirms your period. If you do 1 minus 0, you'll get a 1. That confirms your period here of 1. We want to be looking next at the range. Remember, the range represents the height, the lowest to the highest point on the curve, and I showed you how we can do that. You just do d minus the absolute value of a. Here I'm not capitalizing a. And you can do d plus the absolute value of that a. Plug in these d values. What do we get? Our d value here is a 2. We get a 2 minus 3, which is my amplitude. What do I get? A minus 1. And then I get a 2 plus 3. What do I get? Is a 5. So what's my range? My range is going to extend from minus 1 all the way up to 5. Remember, the regular sine cosine wave goes from minus 1 to 1. But by means of this effect of this amplitude 3, meaning everything is 3 times as tall, but also the vertical translation, we have a vertical translation here of a d of 2 units. By means of the amplitude and this vertical translation, we get a range of minus 1 to 5. So that's this example shown. Let's look at another example. In this example, we have f of x is equal to 2 sine pi x minus, what should we put over here? Let's put a pi. Do we really need to transform this into this form? We can. We already have an a, we have a bx minus c, we just don't have a d, so this would have been a plus 0. I'll just hop out, I'll put over here a plus 0. So this is already transformed into that standard form. Outright, we have the domain mentioned here. Let's look at the amplitude, always absolute value. It's going to be 2. It's twice as tall as a regular sine wave. What about period? 2 pi over b. What's our b value? It's pi. So it's going to be 2 pi over pi, and that gives me a value period wave, the length of a single wave to be 2 units. Is there vertical translation? No, there isn't. No vertical translation. 0. What about phase shift? Phase shift, that's c over b. And here this does not represent, it's undefined. I'm just using this as a 0. It should be a 0. Phase shift, c over b. What's my c over here? It's a pi. What's my b value? It's a pi. So I have a phase shift of what? 1. How do we know which direction are we shifting? We have a bx minus c. When you have a bx minus c form, you're shifting 1 unit. Your wave is going to shift 1 unit towards the right. If this was bx plus c, right? you would be shifting one direction, one unit towards the left, and then you could present your answer in a -1. But here, because we have bx minus c, we'll keep it as a positive one, meaning a change, a translation to the right by 1 unit. Remember, bx plus c, a change or translation by however many units in the minus answer then. Okay? What else? Interval. Our interval is always bx minus c is equal to 0 comma 2 pi. We can do this calculation in our head. Bx minus 0 equals 0 and 2 pi. What's our bx minus c? It's pi x minus pi equals 0 and pi x minus pi equals 2 pi. So all we have to do is actually calculate this. When we take right here, pi x minus pi is equal to 0 comma 2 pi, and we're solving here for x. If you take this first pi over here, when you're using the 0, you get pi x is equal to pi. You take the other pi, you get x is equal to 1. That's the start of your interval. When you're using the same formula here, but with 2 pi, you do pi x minus pi equals 2 pi. You take the first pi, you get 2 pi you get 2 pi plus pi, you get a 3 pi. When you take the other pi, it divides, you get a 3. And I told you before, the interval represents your period as well. If you take the difference of these, you'll get the same value as your period. 3 minus 1 is a 2, and you're having a period of 2. Good. Let's look at our range values. Range values, you want to look at it in this form: d minus absolute value of a and d plus absolute value of a. What am I going to get? What's my d? Is a 0. I'll get a 0 minus a is a 2, right? And then I'm getting a 0 plus 2. So I'm getting a -2 and a 2. My range of the wave is from -2, lowest point, to +2, the highest point. See that, right? Amplitude of 2, period of a 2, no vertical translation, phase shift of a single 1 unit towards the right, interval 1 comma 3 confirms the period. Determined from this formula, bx minus c equals 0 and bx minus c equals 2 pi. You take this part, run it through those two scenarios, and you get your start and your end point. Lastly, you determine the range using d minus absolute value of a and d plus absolute value of a. It gives you your lowest point and your highest point, which are your range. Domain is always minus infinity, comma infinity. We'll look at some more examples. Let's look at this example. F of x is equal to a half. Cosine is going to be a cosine function. 3x plus pi over 4 plus 3 over 2. It's already converted in the standard format. You have a, b, c, and d components. Remember all of these components. There are 4 of those components which you kind of bring out from your function. So when we look at this, we look at the domain already done. Always minus infinity to comma infinity. Unless your question specifies a specific domain. Otherwise, it's always minus infinity to positive infinity. First thing we want to look at is your amplitude. Amplitude here is exactly the coefficient of your function, which is half. That's fine. It's half as high as your normal cosine wave. The next thing we want to look at is the period, which is always 2 pi over b. What's my b value over here? 3. 2 pi over 3. So a single wave will have, if you remember this, 2 pi over 3 represents 120 degrees. A single wave is only 120 degrees long versus 360 degrees. It's 1/3 the regular period. So this is 2 pi over 3. What else do we want to look at? Phase shift, C or B. What's my phase shift? It's a pi over 4 divided by 3. What am I getting? A pi over 12. There's a horizontal translation of pi over 12 units, but in which direction? Remember, the standard form is bx minus c, which implies a rightward movement. If you have a bx plus c, you're thinking about a leftward unit movement, left. A horizontal translation towards the left. But if you're having horizontal translation to the left, you might as well just put a minus sign over here, because this minus pi over 12 indicates a leftward horizontal translation of your function from the basic function, alright? Next, what do you want to look at? The interval. Let's abbreviate interval as int. You do 3x plus pi over 4. 3x plus pi over 4 is equal to 0 comma 2 pi. You solve x for both of these scenarios, and you get a start and you get an endpoint. If you do 3x plus pi over 4 is equal to 0. You take pi over 4 on the other side, you get 3x is equal to minus pi over 4. When you take 3 on the other side, you get x is equal to minus pi over 12. See, minus pi over 12 represents the start of your single wavelet. And then we want to do the other scenario. 3x plus pi over 4 is equal to 2 pi. Take pi over 4 on the other side. You're going to get 2 pi minus pi over 4. You're going to get a 7 pi over 4. See, 360 minus 445, it gives you 315 degrees. But 315 degrees is the same thing as a 7 pi over 4. 7 pi over 4 divided by this 3 gives you what? 7 pi over 12. If you were to take the difference of these, minus some, you'll get 2 pi over 3. Remember, the interval represents the end and the starting point of a single wavelet, which is also represented in terms of the period. So the difference of this will confirm your period. Is there a vertical translation in this function? There is a 3 over 2. You know, to determine the range, we're looking at the effect of the amplitude and the vertical translation. And you're looking at it in terms of this d plus minus the absolute value of a. Here I'm just combining the both scenarios, the lower end and the higher end of that wave in terms of this form. It's the same thing as we've been doing before, but I've just condensed it. What was my d value? It's 3 over 2. What's my a value? 1 over 2. Absolute value, here absolute value is not very applicable because we're dealing with a positive number. But what will my range be? It'll be just the result of this calculation. 3 over 2 minus 1 over 2 gives you a 2 over 2, which is a 1. The lowest point on this curve is no longer a minus 1 because the effect of this 3 over 2 and the shortening of the wave has brought you above the x-axis line. So you have no point on this function which is even in the negative y zone, alright? And then 3 over 2 plus 1 over 2 is giving you a 4 over 2, which is a 2. That's your range. The lowest point on this curve will be no lower than 1 and the highest point will be no higher than 2. So it's going to be a curve which is half as high, half as tall as a regular cosine function, but it'll be shifted upwards by 1.5 units. So here's another example laid out for you. I say let's do one more example and then we'll wrap this video, making everything clear with this final example. I have a sine function over here. F of x is equal to 2 sine, let's throw in a parentheses and let's say x over 3. How about a minus pi, and let's put a, let's put a 4. Make it more interesting. We're looking at the effect of these components over here. The first thing I want to do is point out again the domain is that minus infinity comma infinity. Next, let's look at the amplitude. Amplitude again representing how high our wave is. Amplitude is the coefficient of your function, which here is a 2. If absolute value of a equals 2, you know in reality a equals what? Plus and minus 2. So if there were no if there were no vertical translation, your wave would go as far down as minus 2 and it would go as far as up plus 2, which would kind of indicate your range. But by means of throwing in these vertical translations, the effect of this is kind of spoiled because we've added a translation on top of this. What's the next thing you want to look at? Period. 2 pi over b. Always remember 2 pi over b. Here, what's my b value? The b value is always your coefficient of the variable. Variable here is x, but my coefficient is really a 1 over 3. Flip this around, what do you get? 6 pi. My wave happens to be not 2 pi, which is the regular period of a sine or a cosine. It's 6 pi, so it's 3 times as long. If it's 3 times as long, the frequency of this wave would be 3 times as short. Remember, a longer wave, fewer number of times, it will cycle through a given point. So it'll be a lower energy wave, but a longer wave. 6 pi is my period. What do I want to look at next? Phase shift, C or B. What's my C value? Pi. Don't put in the minus sign. We'll worry about the effect of that as I've shown you with each example. If it's towards the right, you keep it positive. If it's towards the left, you make it minus. Here my C value is a pi. What's my B value? 1 over 3. Flip it around. What do you get? 3 pi. Right? You have a phase shift 3 pi, but in which direction? Your wave has shifted by 3 pi units, but it's shifted towards the right. Why is it shifted towards the right? Again, look over here, bx minus c. And you have to think of it in terms of this bx minus c, or As you remember back in parabolas, x minus h. X minus h represented a move to the right. X plus h represented a move to the left. So if you have a movement to the right, just keep your answer exactly as you get. A positive answer, a positive 3 pi. So we have a phase shift of 3 pi units to the right. What's next? It will be our interval. Our interval should be second nature by now. Just do x divided by 3 minus pi and equal all of this into two items, 0 and 2 pi. And you have to individually calculate for x over here to get your start and your end point for each wavelet. When you do x over 3 minus pi equals 0, you take pi on the other side, you get x over 3 equals pi. You take 3 on the other side, you get 3 pi. See, you get 3 pi because the 3 multiplies, cross multiplies upward. Then when we're looking at it in terms of the 2 pi, x over 3 minus pi equals 2 pi. You take pi on the other side and adds with this 2 pi and you get a 3 pi. X over 3 equals that 3 pi and the 3 goes on the other side to give you a 9 pi. Right? It multiplies to give you a 9 pi. And you know now the difference of this is equal to your period. 9 pi minus 3 pi is 6 pi. But this interval is important because all the important points you need to know with regards to the start and the end and everything in between can be represented alone by all the necessary points on this interval. And this interval confirms your period. We have a vertical translation here of 4. This vertical translation along with the effect of this amplitude will finally give you your range. And you know we're looking at it in this way. D plus minus absolute value of A, capital or lowercase, it don't matter. What's my D over here? It's a 4. What's my amplitude? Is a 2. Let's run this through and we'll finally have completed this. And my range will be shown right over here. Always in square brackets because these points actually are on the curve. 4 minus 2 is a 2. 4 plus 2 is a 6. So the lowest point on the curve, sine curve, is 2 and the highest point on this sine curve is a 6. A difference of this, you can see there's a 4 over here. But you can see if you were to graph this, you'd have a graph which is twice as tall. It would have been moved up by 4 units. The basic point that you would use as your reference point on the sine curve, the basic sine curve, will have shifted toward the right by 3 pi units. Each wavelet would be 6 pi, meaning it would be 3 times as long as your regular sine curve. And you'd have a very important interval represented by 3 pi and 9 pi, the start and the end of that wavelet. And you got your range, you got your domain. And everything all basically falls down from your being able to convert each of these functions into this form from which you derive all of these aspects. So keep this function in mind, perhaps one of the most useful and important trigonometric function analysis video I'll ever show. So keep the effect of A, B, C and D in mind, sine and cosine being more important because they're more commonly seen. So I hope you've enjoyed this video. Feel free to look at it several times because it will only be to your benefit. Like, subscribe and share. Thank you for joining me for this video. Please have a nice day. Bye.